We're taught that gravity is an invisible tether, a constant, downward-pulling force that anchors everything to the planet. But Albert Einstein offered a different explanation. He realized that the physical sensation of being pulled downward is indistinguishable from standing on a floor that is accelerating upward. In this framework, gravity is a misinterpretation of our surroundings. Instead of a tether pulling us down, the ground is rushing up to meet us. Inside a flat room, the math checks out perfectly. But when we apply that same logic to an entire planet, the geometry appears to shatter. To see the problem, we have to look at Earth as a closed spherical object. If the ground in New York, the Australian outback, and both poles is constantly accelerating upward to meet our feet, then the surface of the planet must be pushing outward in all directions simultaneously. Since the Earth is clearly not ballooning in size, we're left with a stark contradiction. Either the model is wrong, or our brains are missing a crucial dimension of reality. Resolving this contradiction requires us to look at a mechanism called gravitational time dilation. We often treat time as an unchanging background clock, but near massive objects, it behaves like a flexible physical property. Because your head sits further from the Earth's mass than your feet, the top of your body ages slightly faster than the bottom. We measure this temporal distortion constantly. The clocks on board GPS satellites drift so significantly relative to the surface that if our networks failed to account for the altitude difference, global navigation would lose accuracy within minutes. This means that time is a physical fabric that massive objects can actively distort. Imagine a flat spatial grid rolling into a cylinder. The horizontal axis is space, the circumference is time. A stationary object loops the circumference, moving only through time. If it shifts horizontally, it traces a stretched spiral, covering less time. Relativistic physics treats this as a zero-sum game. Everything in the universe moves through space-time with a combined budget equal to the speed of light. Because that total speed is constant, any distance you cover in space is essentially subtracted from the rate at which you experience time. When we place the mass of the Earth into this cylinder model, we can observe how that time budget changes. We know that clocks closer to the planet's surface tick slower than clocks at higher altitudes. To maintain a constant speed of light path as time slows, the geometry stretches. The cylinder widens near Earth, forming a cone. Completing a temporal loop at the wide base requires more distance than at the top, visualizing slower time. The presence of mass warps the local geometry of time, forcing the straight lines of the universe into the curves we perceive as gravity. We can finally resolve our paradox by translating this three-dimensional cone back into a format we can easily read. If we unroll the cone, we see the true path of the ground through spacetime. On this flattened map, the lines sweep upward, mathematical proof the ground is accelerating. Crucially, despite this upward curvature, the distance between opposite sides of the Earth remains fixed. Time curvature provides the geometric loophole required for a surface to accelerate outward in spacetime, while its physical volume remains unchanged. This explains the mundane experience of watching an apple fall from a tree. The apple follows a perfectly straight, unaccelerated path through spacetime. We only perceive it as dropping because we are observing it from the vantage point of a curved, accelerating surface. While popular analogies suggest that space pulls us down, the reality is the opposite. Gravity is the curvature of time pushing the ground up to meet us.